said, particularly this evening at the dinner, get your retaliation in first, Prakash. That's very nice. But I think now we're all here, so we can start with the talks. This is going to be a scientific meeting. I'm sure there'll be the odd reminiscence and joke along the way, but there'll also be, I think, a lot of science here as well, and also the volume that you have now, Prakash. So anyway,
open it now.
well, let's do.
Oh,
Yes.
okay.
Well, you have to be checking the proofs. So, okay, so let's begin with, so we have two talks now, and the first is going to be given by Mislove. Mike, you would very much.
Oh, great water. Well, thank you. So actually, I have a couple of things to say before I start saying anything scientific. So it's obviously relevant to Prakash. The way this started, and I think it's important to explain to people how this evolved. Jan Rutten approached me, I've forgotten how long ago, maybe a year ago, and said he and Alexandra were thinking about doing something for Prakash for his 60th birthday. And I think you know MFPS, which is a conference I'm involved in, has a history of honoring people on significant birthdays, and asked, could they do a special session at MFPS? And I thought about it, and I realized a special session is usually a plenary talk with 4 lectures. And if you look around this room and you look at the program, we'd have a massively parallel session so that everybody have 5 minutes to say something. So I decided that we really couldn't do it as part of MFPS. And I also knew that Samson and Prakash are very close friends, so I approached Samson about how can we organize something either co-located with MFPS, but no, that's no good because it's going to be a week long and nobody will come for a full week. That's wrong, actually, but never mind. So then we hatched the idea of running a workshop separate. And so somehow it fell to me and Samson and Bob to organize the workshop. And Jan and Alexandra recruited Elham and Katusha to help with the editing of the volume. And I think that alone says something about Prakash and his influence. It takes 7 people to organize something for you. Pay attention. I'm talking about it. So Elham very eloquently talked about the personal experience of knowing Prakash and having him as a mentor. I've been sharing a flat with Prakash this week, and I've learned a little bit about the peculiarities of sharing a flat with somebody of Indian origin. First night of the spring school, there were some drinks here. On the way home, Bart and I and Prakash went to dinner, and who else was there? Phil. Oh, Phil Scott, right. And they said, oh, let's go get some Indian food. Okay. So we walk up Banbury Road and get some Indian food. We get back to the apartment, and there's an email from Bob. Let's do Indian food tomorrow on the Cali Road. How about it? All right, 2 nights in a row, not bad. We're in the process of answering that when Joel says, come on over for dinner on Wednesday. We'll get Indian takeout. So I put my foot down and said, enough. So we had pizza. The next night we get home a little early. We're not in the apartment more than 5 minutes. The TV's on. Really? Prakash is watching cricket. I think I look suitably unimpressed because he hasn't turned it on again. Okay, so with all that, it's been really fun this week, and we should do this more often.
Yeah, I like it.
Next time. Right. So I'm going to go ahead and start this talk now. But I should say as well that this talk evolved from a comment that Prakash made at a dog school meeting that Samson and I organized about 1.5 years ago. The talk I gave was pretty inscrutable. I'm not even sure what it was meant to do. But at the end I made a comment about the relationship between Haar measure on the Cantor group, or a Cantor group, and the Lebesgue measure on the interval, and how through some domain theory you could see one maps to the other. And Prakash was really impressed with it. He thought, oh, that's really neat, that bit at the end. It's probably the only coherent thing. So I put it together into this, and it turned out to be a little more involved. And it turns out at the end of the day, you get a little more out of it, too. Get out of there. So let me try to tell you about this. So let me begin with Lebesgue measure in the unit interval. Lebesgue measure, you know, is the measure we all use on the real line. And it just measures an interval by its length. Take the difference of the endpoints. A notable property of it is the fact that it's translation invariant. If you take a measurable set, a Borel measurable set, and translate it, add something to it, the measure with respect to Lebesgue measure doesn't change. So there's a reason for this. Well, there's an explanation, I should say. There's a theorem by Haar from 1933 that says every locally compact group has a unique up to scalar constant left translation invariant regular Borel measure, mu sub g, which is called Haar measure. And so the reals under addition is a locally compact group. The addition and negation are continuous operations, and it's a group structure. And so Lebesgue measure is the Haar measure, if you like, on the real line under addition. And so the theorem says every locally compact group has a unique such measure up to scalar factor, because you can multiply by a scalar. Intervals are twice as long as we think they are. I think you used the term 17, the number 17 yesterday. Not sure why, but anyway, you can change the scalar, but things won't change. It's normal to assume that if you've got a compact group, since compact sets have finite measure, to make that measure 1. So in particular, for example, the circle group has measure 1. That's the torus, or R mod Z, if you like to think of it that way. And you take the image of Lebesgue measure from the reals and transport it by the quotient map, and you get Haar measure on the circle. It turns out for a finite group, every finite group is locally compact in the discrete topology, in fact compact, so you take counting measure and normalize it. Okay? So this is basic harmonic analysis. So there's an interesting construct from inside the unit interval, well, we'll talk about the middle third Cantor set, and I think most of you know this, but just to recall, you start with the unit interval and take out the middle third, and you end up with two intervals, each of a length a third. You go inside them and do the same thing. And you continue that, and then there's a theorem that says if you take a descending family like this of closed subsets of a compact Hausdorff space, the intersection is non-empty and compact, and closed, hence compact. So this is compact. It's zero-dimensional, which means that there are no non-degenerate connected subsets. And if you count up the lengths of the intervals you've taken out, you'll find the sum is 1. And so what you have left has Lebesgue measure 0. Okay? So this is standard. This space, the Cantor space, the Cantor set, middle third, you can do it in other ways as well, is, as a topological space, unique for the properties that it's compact Hausdorff, totally disconnected, zero-dimensional, they're the same thing. Second countable and perfect. Perfect means every point's a limit point. Okay? So you understand what that means. So any point has the property that in any neighborhood there are other points. There's no points that are isolated topologically. Okay? So actually there are group structures you can put on the Cantor set. So one of them is just take the two-point group, Z2, take countably many copies of it. Topologically, if you give Z2 the discrete topology and take the product, then what you have is a compact Hausdorff space that's second countable, totally disconnected, every point's a limit point. It's got to be the Cantor set. So it's homeomorphic to the Cantor set. It's another version of it. Here, the measure, let's see, what I said a minute ago, is that any finite group has the property that the Haar measure is normalized counting measure, so, and the measure of Z2 itself, since it's compact, is 1. And then you just take the product measure, And you can do that here even though you have infinitely many copies because, remember, an open set, for example, is restricted in finitely many components in the whole space and everything else. So every component is bounded by 1, so this product will converge, this infinite product, if you like. So this makes perfect sense. And the product measure is the Haar measure for the product space. A remarkable fact about the Cantor set, which is what drove analysts rather wild at the time when it was first discovered, was if you take the map from the Cantor set to the interval and extend it to the whole interval. So what you're doing is you're shrinking the endpoints of the intervals you took out. So the two endpoints, the endpoint at 1/3 and 2/3 are identified and they're sent to a half. And between 1/9 and 2/9 you go to a fourth. Between 7/9 and 8/9 you go to 3/4 and so on. You get a continuous map from the interval onto itself that's not constant. In fact, it's onto the whole interval. But its derivative almost everywhere is 0. And analysts had a lot of problems with that when it was first discovered. But there's a nice theorem of Schmidt's, Wolfgang Schmidt, I think is his first name, the person who did Diophantine approximation and Schmidt games, that tells you that this map, if you restrict to the Cantor set, and you regard the Cantor set as the product of 2-point groups, Haar measure on the Cantor set maps to Lebesgue measure on the interval. Seems bizarre, and in fact remarkable, however you want to think about it. And so this was known, I mean, it's almost a folklore result. I have two colleagues from Germany, one of whom, when I told him this, said, I don't know that result. And the other of whom said, oh, everybody knows that. When I commented that our mutual colleague said he didn't know it, wasn't even sure it was true, he said, oh, he's just having a senior moment. Get used to that, So what we're going to do today is to generalize this to any group structure you can put on the Cantor set, okay? Which is sort of interesting. So what sort of group structures do we have on the Cantor set? Well, I already told you one, just the product of 2-point groups. You can actually take any family of, actually finite groups at all, but let's make them abelian, say cyclic groups. Any product of them, that's another Cantor group. Compact, zero-dimensional, perfect space. The Haar measure on this is the product of the Haar measures of, on each factor. Just take the product measure. An interesting one, we'll come back to this toward the end, is what's called the p-adic integer. So instead of using the product structure, what you do is you map from one of these to the next, not by just projecting off the last component. You actually use a map that sends, in this case, x to x mod p. If you do it multiplicatively, you take x to the p. That gets you from one a cyclic group of order Pn plus 1 to a cyclic group of order Pn. Okay? And the limit of this is Cp infinity, the p-adic integers. That's another Cantor group. Now, these are all abelian. You don't have to do things abelian. You can take the symmetric group on n letters, for example, for each factor. You can repeat the same factor over and over again if you like. But that's not abelian. And so now you've got a non-abelian topological group structure on the Cantor set. So there are lots of these. So what we'll call by, what we'll say a Cantor group is this, a compact, zero-dimensional, second countable perfect space, i.e. the Cantor set, endowed with a topological group structure. So algebraically it's a group and the operations are continuous. Here's lots of ways you can get some. Okay? Have I lost everybody, or nobody's even going to say anything? Okay. All right, so here's a...
Is that a standard notion of Cantor group, or are you introducing?
Yeah, no. I mean, it's if you say you walk into a room of mathematicians and say, oh, a Cantor group walks into a bar, they don't know what you're talking about. That's true. No, I mean, if you Google Cantor group, you'll see it. This is okay. But you haven't identified which one. There are lots of them. That's my point. Okay. So what can we say about the Cantor group? Well, we know that the Cantor set is a stone space. So stone duality says it's the spectrum of a Boolean algebra, take the Clopin subsets. Another way to realize that is to say that it's an inverse limit of finite sets. Okay, countably many, in fact. But in fact, even more is true. The method I used to show you how to get some is in fact almost the only way you can get them. And that's what this theorem says. This is a standard result. If you take a compact zero-dimensional group, I should say perfect as well, since I don't want finite. If it's finite, it's trivial. Then it has a neighborhood basis at the identity of Clopin normal subgroups. Okay? Which is to say, you have normal subgroups that are closed, you can take the quotient group and you'll get another compact group. And since it's Clopin, and that means it's open and closed, the quotient of a compact set by an open set will give you a finite set. Okay, so each of those quotients will be finite groups. Okay, and here's a proof. I won't go through it. It's just massaging the properties of the group structure on this space and using Clopin sets. So the first thing you do is show any neighborhood has in fact a subgroup. And then what you do is once you have a subgroup, you inside it, you form a normal subgroup, and it's also Clopin. Okay? All right, so...
Mike, what's that phrase, at the identity of mean?
Oh, the identity of the group. So in a group, the whole topology is really generated by neighborhoods of the identity, because the translations are homeomorphisms. If you translate over here, translate by the inverse and go back. So that's always a homeomorphism. Inversions are homeomorphism as well. So in groups, life is very, very nice. So if you know what the topology looks like at the identity, you know what it looks like everywhere. Okay? And so this is telling you that there are open normal subgroups. Well, every subgroup has to contain the identity. Since they're open, those are neighborhoods of the identity. And you can write the identity as an intersection of a filter base.
So you're saying it's uniquely determined by what happens at the identity of the group?
Yeah.
Yeah.
Okay. Yeah, the identity I mean, I'm referring to here is the group identity, the identity element. Okay? That's, as it were, that's where all the action is in a group. Okay? No fun. Anyway, so this is just a brief thing that I'll include if we're putting slides on a line or something. Okay, so let me tell you two theorems. So that says every compact zero-dimensional Cantor group, every Cantor group can be expressed as an inverse limit of finite groups. That's nice. That's the corollary of this theorem. There's a theorem by Fedorchuk from 1991, I believe. And what it says is if you have a compact space X, compact Hausdorff is what I'm working in here, that's an inverse limit of compact Hausdorff spaces, then the probability monad on it is continuous. So the probability measures on X, that family is isomorphic to the inverse limit of the probability measures on the spaces X sub I. Okay, so that's a very nice result. So in a sense, the probability monad preserves inverse limits.
What are the, where is that isomorphism living?
Well, that's an interesting point, and we'll talk about that. This is just in topology right now, topological spaces.
And you're putting a topology on the set of probability distributions.
Yes, the weak star topology.
Right.
Okay. All right. So as in the unit ball dual.
So it's like it's sort of in the version of the Shearing monad
Yes.
with topological spaces.
Right. Okay. The other thing I want to point out is that, and this is an easy exercise, if you have two topological groups G and H, and you have a homomorphism from G onto H, then Haar measure on G under this map. So what is probability of, is there something I can write with other than? That's what these are. So just to recall, I don't think I wrote this in my slide, but what do I mean? So I have phi from G to H. So prob of phi from prob of G, prob of H is given by prob of G of phi and a measure mu as set A. So A is a measurable subset of H, Borel set if you like, is mu of P inverse of A. Okay? So it's the usual push forward of the measure that you should be used to. Okay? So the point is the probability monad is covariant, and that's what I'm using here. So in particular, the Haar measure on G actually maps to Haar measure on H. Okay? So not only is the probability functor continuous, maps probability measures on X to probability measures on the X of I's, this isomorphism here. But in the case of groups, this mapping will actually take Haar measure to Haar measure. And so what you can say then is a corollary, and this really gets to what Samson was asking, was that if these X of I, this X and the X of I's are compact groups, then the Haar measure on G is in fact the limit of the Haar measures on the GI's. Okay, so life is really very nice. Okay, so that's a little bit of group theory and probability measures on it. And so what we can summarize this as saying is that if G is a Cantor group, then you can express it as an inverse limit of a sequence of finite groups, abelian, non-abelian, doesn't matter. And Haar measure on G, the Haar measure you get, which principle can be different from one group structure to another, is the limit of these mu n's, where mu n is what? Well, guess what? If G is finite, Gn is finite, we already said the Haar measure, the unique Haar measure, is the normalized counting measure. So each of these Gn's has the same Haar measure, so the limit G as, they don't have the same. What I'm saying will make sense in a minute. But anyway, this is still true. Okay? I'm getting ahead of myself. All right. All right. So next point. And this is the main point. It's all about abelian groups. So let me explain what I mean by that. I just explained that you could represent any topological group structure on the Cantor set as an inverse limit of finite groups. But that group structure might be abelian, it might be non-abelian. Okay. What we're going to see now is that, in fact, we can always substitute for any group structure you have an abelian one in a very nice way. And we'll see that Haar measures are the same. Okay? So that says that effectively, regardless of group structure, there's only really one Haar measure on the Cantor set. Okay? So how does this work? Well, let's suppose we have G written as an inverse limit of finite groups. And let's assume by induction that we know how to get an abelian group with the same size as Hn is the same size as Gn. So that's the same number of elements. Okay? Well, since they're the same number of elements, they have the same Haar measure. It's normalized counting measure on that size set. So how do I get the n plus first one? Well, what I do is I take Hn and I cross it with an abelian group. Let's take the cyclic group of order of size what? Well, I've got a map from Gn plus 1 to Gn that's a homomorphism. Well, since that's a group homomorphism, that says that the size of Gn must divide the size of Gn plus 1. In fact, the kernel of that map must have size this quotient. So let's take a cyclic group of that size. And now I've got a cyclic group of the same size, or a product of cyclic groups of the same size as the n plus first groups. So I'm showing you, level by level, how to substitute for the existing sequence abelian groups that have the same size. And now, what do I know? I know that Haar measure on this Hn is counting measure, normalized counting measure. It's the same as the Haar measure on Gn for each n. And H is the inverse limit of these, so Haar measure on H, which is this abelian version of the Cantor group, is the inverse limit of these counting measure, but that's Haar measure on the G's. Okay? So, in other words, there's only one Haar measure on G, regardless of what the group structure is. Take any group structure, look at its Haar measure, that's the one. Okay? All right. So, now a little domain theory, which I'm known to do on occasion. Let's assume we're given the Cantor set as an inverse limit of these finite groups, where each one of them is a sum of cyclic groups. Okay? Just for fun. let's endow HN with a lexicographic order. You know what that means, right? You've got a product. This says direct sum, but direct sum and direct product are the same for finite groups. So you've got a product space on each one. Each one is totally ordered, so now I can give it the dictionary order. And let's do that. Then the mappings from HN plus 1 to HN just chops off the last component. That's a group homomorphism. And there's an inclusion from the HN to HN plus 1 that just injects it in and makes it 0, the identity in the n plus first component. And these are group maps that are in fact embedding projection pairs. Okay? All right. So in other words, from a domain theory standpoint, I can take the bilimit of this family. That's the Cantor set, and it's a chain. It's totally ordered, has all synonyms. The compact elements are the union of the images, the injections pushed all the way up, of the finite groups that are making up this thing. And the co-compact elements are, for any compact element, take the soup of the things strictly below it. Okay, so this is just standard. But one way to think about this is I'm really applying domain theory, but in a group setting. Okay? And actually the stone duality, in a sense, in this particular setting, where I'm using group homomorphisms as the bonding maps, just for convenience. Okay? Once you've done this, well, let's see. I have a map from the compact family here to 0, 1. So what are the compact elements here? Good, I've erased it. This is great. The compact elements are the essentially finite groups all sitting in the limit by injecting them in as trailing zeros from some point on. And from each one of those, I can map it to 0, 1, one of those tuples, by adding these up. Just take the sum where you divide the ith one by the product of the first. These are the ki's that determine the order of the cyclic groups you're taking as factors. Okay? That turns out to be a strictly monotone map. It's not a group homomorphism. I'm just doing order theory now, domain theory. It's a strictly monotone map, and it's therefore going to extend to a Scott continuous map, but it's not hard to check that, in fact, it's Lawson continuous and monotone. So this is the Cantor map from the Cantor set onto the unit interval. Okay? And using that, you can show that if you take an interval in the unit interval, AB, and pull it back by this map, and take Cantor measure of that, the Haar measure on the Cantor set, that's the same as Lebesgue measure on the unit interval. Which is to say that if I take the probability functor and apply it to this map, it takes Haar measure on the Cantor set to Lebesgue measure on the interval. Okay? So there you are. Now, that's a little more that you can say. In fact, if you took two different group structures here, the C I started with an any C prime, where the CNs here are these finite, the GNs are finite groups, then in fact I can take the map from C prime minus its compact elements to the unit interval, and then take the inverse of this map phi that came from C, and map from the interval back to here to get a one-to-one map, because I've left off the compact elements. That is, in fact, a Borel isomorphism. Okay? So that's kind of nice as well. All right. So here's some lagniappe that's not in the paper. So that's sort of the end of the paper. But in fact, one thing that's sort of off-putting, if you like, about this is I'm dealing topologically with Haar measure. And maybe I'd like to see a group theoretic reason why Haar measure on the Cantor group maps to Haar measure, or Lebesgue measure on the interval. And you can do that if you do the following. Remember the torus that I talked about early on? That's the circle modulo the integers. And you know the map. It sends a real number r to e to the 2 pi I r. Okay? And since that's a group homomorphism, it's going to map Lebesgue measure, which is Haar measure on the reals, to Lebesgue measure on the circle. Okay? That's one way to get your Lebesgue measure on the, Haar measure on the circle, rather. Okay? Now, if I decide what element goes to 0, so I'll leave off 0 but leave in 1, that map is a Borel isomorphism. And so Haar measure on the interval is in fact the inverse of this map. Is a map from the torus to the open interval and therefore the closed. And if I look at this inverse map will take Haar measure on the circle group to Lebesgue measure on the interval. Okay? So here's a way to get my hands on Haar measure on the circle from the constructions from the Cantor set in a group theoretic way, not using topological maps but group homomorphisms. Let's take the p-adic integers. I talked about those early on. The bonding maps here take Zpn to Zpn plus 1 to Zpn by this map, and those are group homomorphisms. Each one of these groups is a cyclic group. If I send the generator to some point in the circle, then I sent the whole group into the circle. That's what cyclic groups are about. Once you send the generator somewhere, you know where to send everybody else. And that's where I'll send the generator. And if you do this, you get a family of maps from ZPNs to the circle that are related one to the other. And so that map will extend to a group homomorphism of the Cantor set realized as the p-adic integers to the torus. And since that's a group homomorphism, it sends Haar measure on the Cantor set to Haar measure on the torus. And now I can use this map I got up here to go down this way to get Haar measure and then pull it back to the circle here. And that's the same as the topological map I talked about first. Okay? So this is a way to do this, a quicker way, just using group constructions. Okay, somebody I know likes to say, so what? I don't know, maybe you haven't heard him say that recently, but... So what? What do I mean by that? Well, what's that got to do with computation, say? This is all pure math, analytic topology, maybe a little group theory. So, here's what, put it that way. The Cantor fan, you can call it the Cantor fan, the Cantor tree if you like, is in fact a finite or infinite words over a two-point set. And you can think of it as the outcomes you get by flipping coins. Okay? So, and the reason it's called the Cantor fan or the Cantor tree is the set of infinite words is the Cantor set. Okay? And here you use the prefix order. S is below T if S is a prefix of T. The maximal elements are homeomorphic to the Cantor set in the relative Scott topology as a domain. Okay, so this is an algebraic domain. The compact elements are the finite words. That's domain theory, kindergarten level. Okay. We also have the interval domain. Take the set of closed intervals in the unit interval under reverse inclusion. That's a nice domain. It's not algebraic, but way below is containing one interval in the interior of another. The map we have from the Cantor set to the unit interval, well, the Cantor set is the maximal elements of this domain. The unit interval is the set of maximal elements of this domain. And you can then take this map and induce from it a Scott continuous map from the Cantor fan onto the unit interval. And that map you can apply the probability functor to, and it'll take probability measures on the Cantor fan and probability measures on the interval. And in particular, we know that Haar measure is the image of, Lebesgue measure is the image of Haar measure on the Cantor set. That measure, which is on the maximal elements, actually is the limit of the Haar measures on the finite parts of the Cantor tree as you're walking up the tree. Okay? And those are mapped under this map to the weighted sum of point masses at intervals. Why are these point masses at intervals? Because I'm in the interval domain. Okay? So what does this tell you? This tells you that you get Lebesgue measure on the interval as a very nice limit using the Cantor construction. Okay? It's not anything new. I think people know this, but I'm doing it in a domain theoretic way. Well, that's nice. Can we get anything else? Yeah. There's a theorem of Storahad. This is not really the full theorem. It's only one special case. But it says if you take a Borel measure on the unit interval, then there's a measurable map from the interval to itself, satisfying the fact that it maps Lebesgue measure to that measure you chose. Really amazing. Well, I know how to get the Lebesgue measure as a limit in a nice way of finite measures, simple measures. And this will then tell me how to get any measure as such a limit just by composing with this map C sub u. Okay. So that says I can get any measure in this way. So in a sense, Lebesgue measure generates everything. That's what the score Haar theorem is saying. The one thing missing out of this is, can you make this map stock continuous? I believe you can, but I haven't done proof, at least for regular measures. This says any Borel measure, whether it's regular or not. But I think you can do it for regular measures, in fact. Okay? All right, so that's what. And finally, happy birthday. Thank you.
So we're told I have to ask a question after every talk, just like Samson did last year. But this time it's a genuine question.
You care to respond?
Unlike Samson and me.
Unlike the ones I'm going to ask the next 39 talks. So as you might know, with a couple of the guys in the row behind me, and my former student Philippe, we've been constructing approximations of Markov processes. And one of the theorems you quoted is actually closely related to the theorem of Choksi, who, curiously enough, was my neighbor two doors down from where I lived in Montreal. Anyway.
Is that relevant?
No, not relevant. Rambling.
It's okay.
But one of the things that we've been missing in our approximation theory is constructing a measure on the limit space. We proved that you've got a limit in the measurable category.
Okay.
We haven't been able to actually transfer the measure, and I'm wondering, so one thing that's been missing completely in our ideas is the group theory that you've been showing us. I'm wondering if using Haar measure ideas, we might be able to complete that program.
Well, I
Because it's exactly like this. It's like a
yeah,
stone.
I don't know the detail. I haven't read the paper. Sorry. I'd be happy to read it. I'd have to look. But yeah, I mean, the thing up here is that, in a sense, the Cantor set's sort of universal. You can map it onto the interval, and from the interval, you can get to any measure. The Skorohod's thing talks about, his full theorem says you take not only a measure, but a Borel measure on a Pauli space, you can actually realize it in the same way. And actually, if you have a sequence converging to it, almost surely, I think, then you can get random variables whose laws are the sequence, and the law of the limit is the limit of the laws. This makes sense, actually.
But it sounds very powerful.
It is, it is. So, and trying to understand that is what I'm working on. But yeah, I mean, you could...
We've been trying to use martingale convergence theorems and things like that.
Oh.
Not getting there.
Okay. Well, let's look at it.
Yeah.
Yeah. Okay. That was a good question. Another good one.
Any other questions? Yes.
Yeah, so I think a point on this. So you said space is a limit. You can get lots of Haar measures of tangent space.
No, I said you can get lots of group structures, which in principle would be...
But they all give you the same Haar
They give, that's the whole, yeah, so that's the point of the talk. That they all have the same, exactly the same Haar measure, and in fact, if you look at the map from one of them to the unit interval, and you can bring it back, you can construct a Borel isomorphism from this version to that version.
What's sort of the optimorphism?
Yeah, yeah.
And see, I mean, that struck me as an amazingly, it was very surprising. I mean, how is it very specific to the Cantor setting?
Yeah, I think it is. I
There's
think
no
it is
other-
just the structure of the Cantor set is, well, in a sense, rigid. That's one way I can interpret it. Yeah.
Suggests that the groups actually don't play such a role.
Right, right. Yeah, the algebra of the group structure is somehow irrelevant. You have one translation invariant measure, period.
Seems like the profinite structure was
Absolutely driving
Then
that.
the way you were getting the Lebesgue measure in the last part.
Right.
Okay. Any other questions? Yes.
So just following on the last question, do you think it's possible to replace the Cantor group with something with less data, since most of the data there doesn't seem to be I mean, how it's not clear how it's. I mean, you use it, but then it doesn't matter in the end. So is there something left?
Well, it matters in the sense that it says it doesn't matter what group structure you have, but you do need to have that group structure. I mean, for example, how are you going to get the measure on the Cantor set? I showed you, for example, at the start that Lebesgue measure of the Cantor set is 0. So you've got to construct that measure. The obvious way is to realize the Cantor set as an inverse limit of finite sets and use the uniform measure on them. And that's what we're doing. And that's what really drives the whole theory. Okay? So you need at least one, is I think the point. But any other one, it's all the same.